Hi, welcome back to Mrs. Ogram's Maths. In this video, we are doing worked solutions for the Level 3 Calculus paper from 2023, and we are currently on the Algebra of Complex Numbers one, which is 91577. Now, one important thing to note, at the time that I'm recording this, it's before the mark scheme is available. So I've done as much checking as I can, but it is still possible I've made mistakes. Now, when the mark scheme comes out, I will put corrections to any mistakes in the description for this video. So if you do find errors along the way, please check the video description for any corrections that I have in there, or let me know if you spot something else that hasn't been picked up on, and I will add that as a correction in the description. So let's jump in with our first question here. We're going to expand this bracket. So we multiply out those pieces. We've got 5 times 5 makes 25. This here would make a minus 10, and this here would make another minus 10. So we have minus 20 root p. And then finally, the minus 4, minus 2 times minus 2 makes plus 4. The root p times root p is p. So now, just thinking about the form that we want it in the question, I'm just going to rewrite it to match that exactly, to put it into that order. So we are starting with the constant. There's a. The term with the p is the 4p, and then minus 20 root p, so it's in that same format. Part B, we're looking at types of roots to say that this thing here has no real roots, and that means we need the discriminant. So the discriminant is b squared minus 4ac, and for there to be no real roots, that's got to be less than 0. Okay, now the b part of this quadratic is just there, the minus 4. So b squared is minus 4 squared, minus 4 times a is 4, and c is this bit here, like so. And that has to be less than 0 for there to be no real roots. So we've got 16 minus 16 times 3r minus 2 is less than 0. So 16 is less than 16, 3r minus 2. And I'm being very careful with my inequality here to keep things on the right side of it. So if I want to put the r things on the left, I need to reverse the entire thing around. So I'll do that just now, actually. So this would be 16, 3r minus 2 is going to be greater than 16. So if I swap those two over to the other side, I'm turning the entire equation around, so the inequality needs to switch over too. So now 3r minus 2 will be greater than 1. So r has got to be greater than 1 plus 2, which is 3, and then divide it by the 3 is 1. Part C, we're going to start with working out what z over w is in the terms that we've been given. So z is p plus qi, w is a plus bi. And we want to be able to pull out the real portion of that, which means I need to rationalize the denominator first, so that we have everything all on one top line, if you like. So this will times by the conjugate of the denominator, like so. So we have AP plus AQI minus BPI minus BQI squared on the top by multiplying that across there. And on the bottom, we have A squared minus B squared I squared. Okay, now the I squareds are a negative 1. So I squared, that's a minus 1, turn that into a plus. And similarly for this I squared, turns that into a plus there. So now if we just take the real parts, what we can do is rewrite this as AP plus BQ for the real part, plus AQ minus BP times I, all over A squared plus b squared, or in fact we can write it as two different fractions, a squared plus b squared on the bottom of each. So the real part of this is equal to 0. So therefore, this portion here, that's the real part, that will equal 0. So we have AP plus BQ over A squared plus B squared is equal to 0. So therefore AP plus BQ is equal to 0. So AP is equal to minus BQ. And that's what we wanted. On part D, we're told that the first solution of this cubic is that we have 5 minus I. We're looking for 3 roots because we have a cubic. We know that there will be 3. So the second one is an easy achieved mark usually, and that's just to write down the complex conjugate, because roots come in conjugate pairs. So if you have a complex root, its conjugate is also a root. So we'll start with writing that down. Now we can use that to work out the missing piece here in the equation, the d. We know that if these numbers here, the 5 minus I or the 5 plus I, are a root, then we can put them into the equation and it will be true. So if we put 5 minus I in, I'm using the root that's given to us in the question, in place of z, then this equation will hold true, like this. So now over to my calculator, I am going to save myself a bit of work by putting this in as 5 minus, let's get the complex stuff. So 5 minus I, pop that in as my answer. Okay, now we're going answer cubed minus 8 times it squared plus 6 times it, like this. So we have minus 52 plus d equals 0, therefore d is 52. Now we can use that to find the third root. Okay, so our expression now, we have z cubed minus 8z squared plus 6z plus 52 is equal to 0. So, oh wait, no, not equal to 0. We don't need that bit. We're setting it equal to 3 factor brackets. Actually, I'll just move that over ever so slightly. We know this will factorize into 3 factors. The first factor is z minus the first root. The second is z minus the second root. And the third is something z plus a third piece here to be able to make up that factor bracket. Okay, now let's look at what that means by comparing coefficients. So for the z cubed terms, we just check there, we've got z cubed compared to what we can make as z cubed on the right. Okay, so those are the pieces that would make z cubed on the right. The z times az, and that makes a singular z cubed. So a must be 1, because that's the only way that we can get the z cubed termed out of there. Next, look at the constants. It's always easiest to start with the first term and the last term of a polynomial. So we've done the first term. Now let's look at this last term. The 52 can only be made by timesing together the 3 constants that we have on the right. So 52 will be equal to minus 5 minus I times minus 5. Oh, I've made a mistake, I just noticed. One of those should have been a plus right there. Okay, minus 5 plus I for the other root times by b. Okay, now if we pop in negative 5 minus I times negative 5 plus I, that gives us 26. So this is equal to 26b, and b will then be equal to 2, because 52 divided by 26 is 2. So the third factor, this bracket just here, is z plus 2. So the third root is minus 2. Okay, for the excellence question, let's start. What we want to do is work out what this is and show that it's equal to this. So let's start just with the u over v first. So u over v is equal to 3 plus I over 1 plus 2i. So we go 3 plus I divided by 1 plus 2i. And that's equal to 1 minus I. Okay, next, if we were to do u over v plus k, and the modulus of it, that would be the same as doing the modulus of 1 minus I plus k. Let's make that a bit bigger. There we go. So the real part of that is 1 plus k, and then minus I. Now, modulus means we square root the real part squared plus the imaginary part squared. Remember, the imaginary part is the coefficient of the imaginary. It's not the I itself. So this will be equal to the square root of 1 plus 2k plus k squared plus 1. And then we will set that to be equal to the square root of k plus 2. So at this point, I'm going to introduce that this is equal to the square root of k plus 2. And then we can work out what k needs to be to make this true. So on the left, we've got k squared plus 2k plus 2 is equal to k plus 2. I'm squaring both sides, removing that square root. Bring everything to the left-hand side. We've got k squared plus k. The 2 minus 2 cancels, so now we have that's equal to 0. So k factorizes out like so, and k is equal to 0, or k is equal to minus 1. And I'm just going to double check if there's any restrictions in the question. We haven't got anything like k has to be greater than 0, so those are our two solutions as our final answer there. Question 2, we're doing u over v. It's already in polar form, so that's helpful. This means that we take the modulus and divide them, and the argument gets subtracted. Okay, so q to the 6 divided by q squared will be q to the 4 cis, and then 5 over 8 minus 2 over 5 is 9 over 40, so that's 9 pi by 40. Okay, for B, we want to find the modulus of z minus w. So we're going to do the modulus of, okay, so z minus w is 1 plus ki minus 7 minus ki. Oops, straight line there. So that's going to be the modulus of 1 minus 7 is 6, and ki plus ki will be 2ki. So the modulus of that means to do the square root of the 6 squared plus the 2k squared. So that is the square root of 36 plus 4k squared. Okay, part C. Let's start by calling zx plus iy. Because the reason I know to do that is because I'm going to be looking for the argument, which means that I'll need to find an angle. And for that, I'll probably need the real and imaginary parts separately so that I can work out the angle on a triangle for it. Okay, so if that's true, then what we have is 13x plus iy over x plus iy plus 1 is equal to 11 minus 3i. So then 13x plus 13iy is equal to 11 minus 3i times by x plus iy plus 1. Now, remember we're trying to work out the x portion and the y portion. So that's the real part and that's the imaginary part. So we don't need to go full hog on the whole expansion here. We could save ourselves a bit of effort just by looking at those real and imaginary parts separately. So let's consider the real parts of this. So on the left we have 13x for the real parts. On the right, to get real out of this, we would do 11 times x. We would have 11 times 1, and we can do minus 3y times iy. That would give me 3i squared y. And then the I squared would be equal to 1. So we have, well, 13x, let's move everything to the left-hand side as well. So 13x minus 11x is 2x. This here becomes plus 3y, and then we take it over to the other side, it's now minus 3y. Minus 11 as we take that over to the left is equal to 0. Okay, now consider the imaginary parts. So for the imaginary bits, on the left we've got 13y from this piece just here. And on the right, we can make imaginary parts from this. So this would be minus 3i times x. So the coefficient there would be a minus 3x. We can make an imaginary from this bit. So 11 times iy. So just the coefficient of that bit would be the 11y. And finally, we have a minus 3i times 1. So the coefficient of I there will be minus 3. Okay, now bringing everything to the left-hand side, we will have a 3x plus a 2y plus 3 is equal to 0. Now over to equation solver, and we can put this in as simultaneous equations. We have two unknowns. Now just one thing to spot, this is x plus y equals a constant, so I'm just going to adjust what I've got as my equations over here. So instead of it being the minus 11 on the left there, I'll make that equal to 11, and this one, bring the 3 over to the other side of the equals, and it will be a equals to minus 3. Okay, so our x values are 2x there. We then have a minus 3, then the constant is 11. Then on the second equation, from the imaginary pieces, we have a 3, a 2, and a negative 3. Now we solve that, and we get that x is 1, y is minus 3. So z equals 1 minus 3i. Now we need the argument of that. So we think about where that is on our Argand diagram. We're over by 1, down by 3. So there's minus 3i, there's 1. And we have our z just here, so we need this angle for the argument. Now think about this triangle that we have being made here. The length along that way is 1, the length that way is a 3. That's one of our special triangles. It's on your formula sheet, and the angle that it gives us just here is pi by 3. Or you can use trigonometry to find that. So the argument of z will be negative pi by 3. Okay, part D. I want to use de Moivre's theorem on this one, and to do that I need it to be z equals to something. So move everything over to the right-hand side, and we've got this. Now thinking about that on an Argand diagram, it's going to be over here on the real axis, it's got no imaginary part, at minus 64 m squared. So in polar form, it's got a length of 64 m squared and an angle of pi. So our first solution of z is to do the cubed root of 64 m to the 12, and then cis argument divided by 3. So this is equal to, let's do 64, the cubed root of it is 4. If you do m12 to the third, the 12 times the third is how we sort out that power. A third of 12 is 4, so it's 4m to the 4 cis pi by 3. Now the second value of z happens when those roots are spaced evenly around the Argand diagram. So if our first one is at pi by 3, then the next root would be a third of a circle on from this first one. So a circle is 2 pi. A third of a circle will be 2/3 on from there. So if we're doing 2/3 of pi on from 1/3 of pi, then we end up at pi. So our second solution now will be to the length of it hasn't changed, so it's still 4m to the 4. But the angle now is at pi. Then our final solution, our third one, again the length hasn't changed, but our angle will be from pi, we now add on another third of a circle. Oh, sorry, third of the circle is 1/3 times 2 pi. So from that one, we add on another 2/3, so that it's a third of a full circle. Now that's equal to cis of 5 pi by 3. You're likely to have that marked correctly, but also notice that that has come underneath the axis now. So we're down here past the pi. So then what we prefer to do is think about what it would be if we came at it from the other direction and make it a negative. So a full circle is 2. Take off that answer, and we've got a third of pi, but in a negative direction. So this is the same as if we do 4m to the 4 cis of minus pi by 3. Okay, for part E, we have a locus question, and your key to loci is almost always to start with saying z is equal to x plus iy. Now let's pop that into this modulus. We'll have x plus iy minus 2 plus I is equal to the square root of 3. Now modulus means we're going to do the square root of the real part, which is x minus 2 squared, plus the imaginary part, which in this case is y minus 1 squared. Add them together. Okay, so then that's equal to root 3. And what we have is x minus 2 squared plus y minus 1 squared is equal to 3. Now I'm not going to bother expanding that because that already tells me as much information as I need. It's showing me that I have a circle. That circle is centered at the coordinate of 2, 1. And I've just spotted a small mistake, so that there should have been a plus here. I pulled that out incorrectly from this bit up here. So we've got a plus iy and a plus I there, so factorizing that gives me y plus 1 there. Okay, so I have a circle that is centered at the coordinate of x equals 2 and y equals minus 1, and it has a radius of the square root of 3. So let me just sketch up what that looks like. So let's say there's minus 1, so 2 would be about here. So there's the center of our circle, and it has a radius of root 3, which will look kind of a bit like this. It's not perfect, but you get the idea. This distance here is √3 for the radius. Okay, now back to the question. And we're being told about a straight line with equation y equals mx minus 1. M is real and it's positive. So I've got a tangent, because it also makes a tangent there, to this circle, and it goes through -1 because that's the y-intercept just there. So I'm starting at -1, and I've got a line that goes tangent. Oh, that wasn't very good. Hold on. So through -1 and tangent to the curve, like so. Now, if I can figure out where the line touches the circle, then I can use that to work out the gradient using this triangle here. That will help me to work out m, obviously, because that'll be the gradient of the tangent. I have this line here, which is a √3, because that's the radius. Let's draw that so I can see it a bit better. So that is √3. And then if I think about this triangle here, that's a right angle there because it's a tangent against a radius. This length here is 2 because our circle was at x coordinate 2. So let me just draw out that triangle a bit bigger. We can see what we're dealing with. So we've got √3, 2. Now that's a special triangle. I know that length is 1. It's on your formula sheet, or you could just do Pythagoras to work it out. Now with that particular triangle, that gives me that this angle here is π/6, and this angle is π/3. Now from all of that, what I actually want is this triangle here so that I can work out the gradient of that purple line. So that's this piece here, and I would have an x and a y. Well, using trigonometry, x is equal to cos π/3 because it's x is the adjacent, and adjacent is cos times the hypotenuse. So we've got cos π/3 times 1. The y is opposite of π/3, and sine times the hypotenuse will give me the opposite. So this is sine of π/3 times by 1. Now the gradient will be equal to the change in y over the change in x. So that's sine π/3 divided by cos π/3. Those are things that we have exact values for. So sine of π/3 is √3 over 2. We're dividing that by cos of π/3, which is 1/2. That cancels to √3. So then back to our final thing, putting that all together, the tangent equation then is equal to y equals that gradient, √3, x minus 1. So final thing, find the value of m. M equals √3. All right, question 3. Okay, so we've got a polynomial gets divided by x minus 3 and the remainder is 30. That means that if we put the value of -3 into our polynomial, we will get the answer of 30. So that's what I'm going to do here and work out what that gives me for p. Okay, so I'm going to put the -3 in first, just save me a little time. So at 2, oh, that is a cubed, not a squared. So 2 times the answer cubed plus 7 times the answer minus 3 gives me minus 78. This bit here is a 9p. Minus 78 makes 30. So if I do 30 plus 78, we've got 9p is 108. So p is 12. Okay, we've got u and v. We're told that u divided by v is 3 plus 4. We want to find the value of n. So if u over v makes 3 plus 4, then u is equal to 3 plus 4i times by v, 2 minus 3i. Let's go over to the calculator for that one. So 3 plus 4i times by 2 minus 3i is 18 minus I. Now match that up to what we were told what u was. U is n minus I, so the n is in the same position as the 18, so n equals 18. Part C, we want to rearrange this to be x equals something in terms of w. So let's start by squaring both sides, and we'll get the following. So the 4 gets squared, and squaring the square root removes the square root sign. The whole of the right-hand side needs to be squared, so I'm going to actually write that out as 2 brackets to make sure we don't miss any pieces. So if we multiply that out, we get 25 minus, this will give us 5 times 8 is 40, so it'll be minus 40 root x, and then another one from this one, so it'll be a total of minus 80 root x, plus the 8 times the 8 is 64, and the root x times the root x is an x. Over here we have 16 times 4 is also 64. So we've got 64x minus 16w. That 64x there cancels with that one. Bring the x over to the left, and we've got 80 root x. And take the minus 16w over to the right to make it a plus 16w. Root x is then 25 plus 16w over 80. So x is 25 plus 16. 25 plus 16w over 80 squared. Part D, we're going to start by trying to pop this this piece here over one denominator. So put it all over 1 plus pi. To turn 1 into something over 1 plus pi, that also needs to be multiplied by 1 plus pi, and then minus the 1. Now this one cancels with this one, so we would end up with bringing this one up here and multiply is 1 plus pi, and this one up here and multiply is equal to pi x plus yi. So we have that expands to xpi plus ypi squared, which is xpi minus yp, since I squared is minus 1, stays equal to 1 plus pi. Now let's look at the real parts of that. So the real parts on the left is 1, on the right is minus yp. So in that case, we have 1 is equal to minus yp, so y is equal to minus 1 over p. And now if we look at the imaginary parts, we have a pi is equal to an xpi. So pi equals xpi. So p equals xp. or x equals p over p, which is 1. And finally, our last excellence question. So what I'm going to do with this one is use this piece to get z in terms of the other parts and substitute it into here to match it with what that's equal to. So that's where we're aiming for. Let's start with this first bit here. So I have that if I bring all the z's over to the left-hand side, I've got z minus iz is equal to k minus 2i. That allows me to take a factor of z here. So that's equal to k minus 2i, so that z on its own can be expressed as k minus 2i over 1 minus I. Then from this bit, we can rewrite that as w equals 2 plus 2i times z. So that's 2 plus 2i times the z that we just worked out, k minus 2i over 1 minus I. So subbing that into there. So multiplying that through, we have that w is equal to 2k plus 2ki minus 4i minus 4i squared, all over 1 minus I. Now take the real parts of that. We've got 2k plus 4, because this bit here, minus 4 times minus 1 becomes a plus 4. And the imaginary part is 2k minus 4 times I from these two terms just here. That will be all over 1 minus I. Okay, now if I just bring that over to the left just a little bit, what I'm going to do next is multiply by the conjugate of the denominator, because what I want to have is this in the form of a plus bi, so I can pick out the imaginary bit and match it to this. So that's where I'm going to next. So if we multiply through that denominator conjugate there, then what we will get is on the top we have 2k plus 4 times 1 plus I, 2k minus 4 times 1 plus I times I, all over 1 squared minus I squared. So we have, expanding that bracket, we have 2k, 2ki plus 4 plus 4i plus 2ki, 2ki squared minus 4i minus 4i squared, all over 2, since we've got 1 squared minus I squared, and I squared is minus 1, so on our denominator that simplifies to 2. Okay, we're getting a bit closer. The 4i cancels with the minus 4i here, and then what we're left with is this one at the end of our expression here. Minus 4 times I squared is a plus 4. We have a 2k. We have, so I just spotted we've got another I squared going on here. So this becomes minus 2k, and it cancels out this 2k here. So 2k minus the 2k. Let me just use a different color here. So that 2k cancels with that minus 2k. We've got a 4 and a 4 there. So we have 8 on the next line down. Let me just get that. So 8 and then plus 4ki all over 2. Or 4 plus 2ki. Now back up to the question, we have that the imaginary part of w is equal to 8. So the imaginary part of W is this piece just here. So that's 2k is equal to 8, therefore k is equal to 4. There you go. That is the complex numbers question paper complete for 2023. Hope you felt good about doing that exam and that this was a positive thing for you to be able to see the solutions to it before the results come out in January. Just one final thing, for those that are watching back the recording later, this video was made before the mark scheme was available, so there's every possibility that I could have made mistakes. I've done as much checking as I can manage without having the answers readily on hand, but if you do find any errors, please leave a comment and I will update them in the video description so that other people can know that when they come to look for these solutions.